Yeah, welcome. I'm Orpheus. This is the Guaranteed Safe AI Seminars, a series on a research program towards AI systems with quantitative safety guarantees. So the session is a little bit under 1 hour. We'll have a presentation. Uh, I mean, it is a pleasure to have you, Samuel. Um
Yep.
Samuel is a PhD candidate at the Institute of Information Security and Dependability at Karlsruhe Institute of Technology. Um, the as you can see, the presentation is entitled "Provably Safe Neural Network Controllers via Differential Dynamic Logic." We can have questions during the presentation. We'll probably have time also at the end for discussion. So thanks so much for being here. Samuel, the floor is yours.
All right. Well, thanks very much for the introduction. Thanks very much for the invitation also. I'm glad to be here. And as it was just said, I'm going to talk about how we can ensure safety of neural network control systems. And the angle from which I'm approaching this is via differential dynamic logic. So if you haven't heard of differential dynamic logic before, that's all right. I'm going to be talking about this and introduce that a little bit as well. And I just want to mention this is joint work with a bunch of people. So I will talk about the original paper from NeurIPS 24 and then also some follow-up works. And this was joint work with my advisor, Bernhard Beckert, but also with some colleagues, Debashmita Loha and also Stefan Mitsch, Angora Prebet, André Platzer, and Matthias Ulbrich. Some of them are at KIT, some of them are at other places. Um, all right, maybe just to set the scene a little bit, what we actually want to talk about. When I talk about a neural network control system, just to give a very simple example of the kind of system that we might be looking at, we could, for example, be looking at a car, basically, where we have two cars. For now, just going to assume the car in the front drives with a constant velocity. And then we might consider the scenario where the car in the back is basically some relative distance, some relative position behind. And we can describe the physical dynamics of the system using differential equations. So, for example, we can say that the relative position evolves according to the relative velocity of the two cars, and the relative velocity of the two cars, again, evolves according to the relative acceleration between the two cars. And in this case, we're going to assume that this relative acceleration is determined by a neural network in the car in the back. So basically, the car in the back can either accelerate or can brake. And based on this decision, we're going to have a change in the relative position. And this all happens continuously. And importantly, what we would like to guarantee is that the two cars don't crash. So essentially, we want to ensure that this relative position right here is always going to be positive. And now the question is, how can we guarantee this on infinite time horizon, right? So we don't just want the cars to be safe for, let's say, the first 30 seconds or for the first minute of the drive, but we want to make sure that this is safe no matter how long the two cars drive. And now there's a very simple solution to that. And this very simple solution would be that we just train the network in a way that ensures that the car in the back always outputs a very large negative number. And essentially, what this would do is it would make it so that the car in the back brakes really hard. It comes to a halt. The system is safe. But probably that's not what we want, right? Probably we have some secondary objectives that are the reason why we want to use a neural network. So maybe we have some kind of car chase situation and we want the car in the back to actually keep following the car in the front. Or maybe we want to optimize for things like passenger comfort, energy efficiency, and so on and so forth. And suddenly the strategy that this neural network is encoding can be much more complicated. And as it gets more complicated, the question remains, how can we ensure infinite time horizon safety? And the angle, as I said, from which we're approaching this is through differential dynamic logic. And the idea is we want to leverage differential dynamic logic to verify this neural network control systems. Now, there's a bunch of things that I should probably explain here. I've already talked a little bit about what I mean by a neural network control system. I'll also talk more explicitly now about what I mean by a neural network in this particular setting here. And then we'll talk about what we mean by verifying it and what we mean by differential dynamic logic. So let's get started with neural networks. I mean, probably most of you, given this seminar, are familiar with it. In this setting, when we're talking about neural networks, you're really still talking about rather simple architectures, right? So we're kind of still at the foundations in terms of what we can do. Here we're going to look at feed-forward neural networks, where essentially we have a set of layers in the network, and the computation happens through a layered computation, where in each iteration you first have an affine transformation, and then afterwards you have some activation function. And for the implementation that I'm going to talk about later, we actually focused on ReLU activation functions because this keeps the problem more tractable. Now, people have been looking into verifying neural networks for, I would say, about, I mean, there have been some early works, but very actively, this community has been looking at it for about 10 or so years now. Usually when people talk about neural network verification, they talk about a property like this. So kind of you have a neural network, which you're given, and you have some constraint about the inputs and the outputs of the neural network. And what you want to check is whether there exists some witness, some X star, such that basically if you put this X star into the network, the property that you've been given holds. So just to give a very simple example, what this might look like, let's say we have an image classification system and we wanted to always predict a certain output if we're within some minor perturbation of some given image. Then what we might say is we might say we want to ensure that we always predict output k for all x inside some delta ball around an image x0. Now we can formalize this as a property by saying, well, first of all, our input x is going to be at most delta away from this x0. And then we want to check whether there exists any output dimension I, which is larger than k for any given input. What this does is essentially it looks for a counterexample, right? So basically, if we find an X which satisfies this formula here, what we found is a counterexample. And I mean, if you've heard of adversarial examples before, where you put a little bit of grain onto an image, and then suddenly it is predicted as something completely different. This is one way in which you can kind of check whether a neural network is robust to this by basically encoding a property like this. We're going to look at more complex properties later, but just to introduce it a little bit. And so people have mostly been looking into what I would call linear normalized properties of neural networks, which essentially have this structure where we first have a large conjunction over constraints in the input space. And afterwards, we have a disjunction over conjunctions in the output space. So we might say something like dimension 0 is between 0 and 0.1, dimension 2 is between 0 and 0.2. And then we might have an OR between different possible constraints for the output space. And so there has been a yearly competition for a few years now, which basically tries to verify such properties on neural networks. And usually what they've been looking at is linear normalized properties. Now, what does all this have to do with control systems? To get to that, we first have to talk about the other bit that I was talking about earlier, which is differential dynamic logic. Now, I assume probably most of you haven't heard of it before, but you can think of differential dynamic logic as a program logic, which allows you to reason about programs. And the programs that we're reasoning about in this case are very specific programs called hybrid programs. Hybrid programs have two kinds of elementary program constructs. On the one hand, you can have discrete assignments. So for example, you could have a variable relative acceleration and you can set it to the value of minus b, or you can have a clock variable c and you can set it to 0, right? I mean, this you can do in any other programming language as well. You have a variable, you set it to some value. The other kind of construct that you have in hybrid programs are continuous programs. And this is something that's not very common in other programming languages. The idea is that you can evolve the state of the program according to a differential equation. So you might remember the differential equation that we had before, where the relative position evolves according to the relative velocity, and the relative velocity evolves according to the relative acceleration. Here we can write a program which states, now our state is going to evolve according to this differential equation. Importantly, here we also have a clock variable, right? This clock variable c is evolving according to the differential equation c prime equals 1. And then we have a domain evolution constraint, which basically says that C is always supposed to be smaller than some constant T. What this does, it basically constrains how long we evolve this differential equation at most. So what this basically means is we evolve the equation at most for time large T. So right now we kind of have a time-bounded system. We first set some variables to some values, and then we evolve the differential equation according to this differential equation here for up to time t. So this is time-bound. What you can now also do in hybrid programs is you can have loops. And these loops basically allow you to go from a finite time horizon analysis to an infinite time horizon analysis by basically looking at all possible repetitions of this program. And since it's a program logic, you can not only just state these programs, but you can prove properties about them. So what you can do is you can put a box around it. If you've heard of modal logics before, this is kind of the idea. We now reason about all possible traces of this program. And you can say that after every program run of this program, we want to ensure that some post condition holds. So essentially what this now states, this is now a formula of differential dynamic logic, and this formula states that if we initialize our variables this way, and if we then run this differential, this differential equation, and we do this repeatedly, we will always ensure that the post condition is larger than 0. Now, if you're very, very observant, you might notice that this is not actually the case. There's another thing that we need to prove this. And to prove this, we need a precondition. We need an assumptions on what kinds of states we're starting in. So for example, in this case, we can introduce a precondition which basically says that initially the relative position of the two cars is large enough that if we now brake really, really hard, we're still able to brake in time to avoid a collision. Now, the idea is we can state these formulas, and then there is a proof calculus and tooling around it, which allows us to prove such properties. And then basically this allows us to reason about symbolic cyberphysical systems. Another important notion here is that while this program here only assigns the relative acceleration to minus b, we can also have non-determinism in these discrete assignments. So what we can do here is we can say either we set relative acceleration to minus b, or we set relative acceleration to b, provided that some condition holds. What this allows us to do is it allows us to not only describe one specific control strategy, like we brake really, really hard in this moment, but it allows us to basically describe what is called a control envelope of possible actions. And so this is actually one key ingredient to what we will be doing later, because basically this allows us to not only verify one specific control strategy, but basically a whole set of control strategies. And this we can then use to analyze our neural network. So the objective for our work is then going to be, we're going to assume that we already have a safe differential dynamic logic model with a controller alpha control, which is this kind of control envelope that I was just talking about. And we have a neural network G. And then the question we're trying to answer is, if we now replace the control envelope alpha control by the neural network G, does the resulting system retain the same safety guarantees that we were able to derive for the control envelope? Now, to do this, we need one more critical ingredient, and this ingredient is called modelplex. The idea of modelplex is that if we have this kind of system where we have a control envelope and then a plant or an environment description, we can take this control envelope and we can derive from it a formula which tells us whether a concrete action would match what our control envelope assumes about the control actions that are being taken. So here we again have a very simple control envelope, which just states we're setting the relative acceleration to minus b. And so we can derive a very simple formula, which checks whether the relative acceleration that we're actually setting satisfies this constraint. So basically, we check whether the new relative acceleration that we're setting is indeed minus b. Now, obviously, we can also do this with far more complicated program control structures, and this then allows us to introduce non-determinism. And so with this, we can basically derive these controller monitoring conditions, which allow us to kind of connect this abstract model that I was just talking about, which we formalize in differential dynamic logic, to concrete control decisions that we might encounter. So how does this connect to neural networks? Let me give you an overview of the work that we basically did on this foundation. The idea is, as I said, is we start off with a control envelope and we assume that we've already proven it safe. And then from this control envelope, from the DL model, and from we're using Modelplex, we derive an open loop verification query for our neural network. So essentially, we derive a very specific property that we want to verify on our neural network. And the property of this specification that we're deriving is that if we're able to verify it, this simultaneously means that the neural network control system is safe. And we do this in a way that we also provide a semantics for what it means for the neural network control system to be safe. Because obviously, a priori, we just have a neural network floating around, right? And we don't really know what is actually the semantics of the system that we're looking at. So we provide the semantics and we provide you with a specification that you can actually check on your neural network to see whether it's verified or not, whether it's safe or not. Now, there's one issue with this query with the specification that we're generating. And this issue is that it actually is more complicated than what most neural network verification tools support, or at least supported at the time when we first started this work. And so we came up with our own tool for neural network verification, which is called, or the approach is called Mosaic. And I'll also be talking about this a little bit. And Mosaic has the special property that allows us to, on the one hand, consider polynomial constraints, which are very common in hybrid systems because you often have nonlinear dynamics, like nonlinear behavior of the system, for example, acceleration, right? And it allows us to consider arbitrary propositional structure, which is also very important for larger case studies. So let me now talk about these two contributions in order, first about Versailles and then about Mosaic. So for Versailles, the idea is basically, as I said, we start off with this control envelope and the neural network. Now, as I said, the idea is we want to define a semantics for what it means for the neural network to be safe. The way we do this is we encode this entire neural network, hypothetically, as a differential dynamic logic program. So we can kind of construct a program which behaves, a hybrid program which behaves exactly as the neural network. Now, on the one hand, we now basically have a program which precisely defines the semantics of the neural network control system that we're looking at. But on the other hand, about hybrid programs, you usually reason about it interactively, but you would never want to reason about this neural network interactively, right? There's all these matrix multiplications in there. You don't really want to deal with that by hand or using your own thoughts, right? You want to automate this. So instead of trying to verify this, we go the other way. We use the model that we already have to derive a specification for the neural network. And the specification roughly consists of, on the one hand, the monitoring formula that I was talking about earlier that we can derive from Modelplex. And on the other hand, it contains an invariant. And this invariant basically tells you which part of the input space of the neural network is relevant. What we can then do is we can try to verify this specification on the neural network. And if we're able to verify it, this is mirrored by a refinement proof from this abstract system to the concrete neural network control system, where basically the fact that we can verify the specification implies that the concrete system is safe because the abstract system was safe. So one might think here the story ends, right? We now are able to generate these specifications, and we know that if we can verify the specification, the system is safe. But as I said, the issue is that these specifications are much more complex than what traditional NN verification tools typically handle. So to that end, we developed a new approach to verification. And I'll first talk a little bit about the properties that we're interested in that kind of come out of Versailles, that come out of this approach. And then I'll explain you how we handle these properties. So there's two specialties about these properties. On the one hand, they have nonlinear constraints. So as you can see here, we have a polynomial in the input space. So we're interested in this region here that requires us to handle this polynomial. And also here in the output space, if we want to prove that we don't enter these red regions, those are polynomials. So we would need some way to handle this. This is the one complexity. The other complexity is that the specifications are typically quite complex in terms of their propositional structure. So for example, we might have different parts in the input space. And as you can see here, for each part of the input space, for case 1 and case 2, we have different parts in the output space that are relevant, right? So we also kind of need to handle this part somehow. The way we approach this is that sorry. The way we approach this is that we first linearize these nonlinear constraints. So what we do is for each of these nonlinear constraints, we generate a linear approximation using existing techniques. And since we already have a propositionally complex specification, we just make it more complex. Basically, for each constraint that we originally had, we add 2 additional formulas to our specification. One formula states if the original constraint is satisfied, then its over approximation is also satisfied. The other states that if the under approximation of a constraint is satisfied, then the original constraint is also satisfied. So we add these piecewise linear approximations. And what we then do is we try to kind of decompose this problem into small linear problems that we can deal with using existing techniques. To do this, one classical approach would be what is called DPLLT. And the idea is that it basically just enumerates all possible combinations of constraints that are feasible. And then we would, for each of these, we would check with the neural network verification tool whether it's satisfiable or not. So for example, we would generate this region in the input space here, and then check whether a neural network verification tool can find a violation because it is contained in this output region over here. And so we would then continue to do this with the next linear region in the output space, and we would move to the next region in the input space again to do it for both regions in the output space, and so on and so forth. Now, as you can see here, in each of these iterations, we are looking at 2 different regions in the output space for one region in the input space. Many of the tools that people use for neural network verification, actually what they do is they take this region in the input space and they do a reachability analysis. So for this reason, it would be much better if we look at one region in the input space and then consider all possible regions in the output space. And this is exactly what we do in our NN verification tool. So it kind of always enumerates it in this way, which gives us a minimality guarantee. And then we can use off-the-shelf tools to check whether they can find a counterexample where we are in this region in the input space and in one of these 2 regions in the output space. There's one issue left, which is sometimes the tool might return as a counterexample, right? So for example, it might return that this point in the input space leads to this value in the output space of the network, or that this point in the input space leads to this point in the output space of the neural network. And since we used linear approximations, it's now not clear whether this is an actual violation. So for example, the lower one would be a violation because we here are actually in the unsafe region, while the upper example would not be a violation because it's actually not inside the region that is deemed unsafe according to the nonlinear constraint. Now, the way we handle this is by using the fact that we're looking at piecewise linear neural networks. Because these networks are piecewise linear, what we can do is we can reconstruct a small region around this counterexample where we know that the network behaves linearly. And so we can reconstruct these regions and then use much more expensive verification tools for nonlinear arithmetic to check whether we have a concrete counterexample. But because we only do this with respect to a linear mapping, we don't care how large or small the network is. We only care about the input space and the output space. So this makes it a lot more feasible. Now, we didn't just think of this approach, we also evaluated it on a bunch of benchmarks. So we did some work on adaptive cruise control and on Zeppelin steering under uncertain wind conditions. But the example that I'm going to talk about today, and which I guess was the largest case study, was on vertical airborne collision avoidance. So the idea behind vertical airborne collision avoidance is that you have 2 planes that are getting closer to each other. One might almost say dangerously close to each other. And as these 2 planes approach each other, there are systems in the airplane that try to warn the pilots and tell them in which direction to fly to avoid a collision. And so there have been some proposals to use neural networks in this scenario. We took one of the systems that people have proposed and analyzed it using our approach. And so just to give you an example, here the plane previously had gotten an advisory to fly down. So it's on a trajectory to fly down, and this would actually avoid a crash. The crash is in this red region here. But now we found that a neural network was actually suggesting to fly up again. And this ascending again would actually lead right into the danger zone and produce a crash. So we evaluated our approach using an existing formalization in differential dynamic logic for this problem and using the neural networks that people had proposed in previous work. And this is actually a system with multiple neural networks that are activated in different circumstances. So we analyzed all of them. And for 2 networks, we were able to give very limited safety guarantees. However, for 6 of the networks, we actually found numerous counterexamples. So for example, in one case, we found over 49,000 regions with counterexamples. Now, what's important to note here is that this system would only be safe if all the networks are safe, because you can't use them individually, you need to use them all together. In this case, we did find some concrete counterexamples. And it's not only that basically our neural network verification tool told us, oh, look, there's a violation of the specification. Actually, for all these 6 networks, we then went and checked whether we were able to reproduce concrete crashes. And sure enough, for each of these cases, we found cases where basically if you were to follow the advisory of the neural network, you would have a crash, while the original path on which the plane was would have not led to a crash. So this was our original work from late 2024, and since then we've been working on some extensions of this work that I'll also briefly review, and then I'll finish up. So the first extension was that actually, funnily enough, right at the start of 2025, there was a conference which holds a yearly case study challenge, where essentially the idea is they give you a system and they tell people, look, throw all your formal methods against it and see whether you can provide some safety guarantees. And so funnily enough, in 2025, the case study was a neural control for a car in the reinforcement learning environment. It was this highway ENV environment, if you've heard of it before. And so we thought, okay, let's see whether we can apply our approach to this. And so they both provided us with this environment and a formal specification document where they wrote up how everything is meant to work. And so we formalized the system in differential dynamic logic and derived an NN specification and tried to verify the system in front of us. And unfortunately, as we tried to do this, we uncovered what we now call a model to simulation gap. So essentially, there were various issues where what was happening in the simulation didn't quite match what we assumed or were given in the specification and the model that we were building. So for example, the specification told us that the action space is working in a certain way, which didn't quite match what the action space was actually doing. And so obviously, we built our DL model from the specification and then noticed, oh, look, this actual simulation is behaving a little bit differently. I mean, this issue you can surely fix, right? Because it's just a matter of like figuring out what the action space actually does. But there were also more curious things. So for example, we noticed that in the simulation, there was actually very, very infrequent braking. And so basically, the cars never really learned to, the reinforcement learning agent never really learned to brake because it happened so seldomly that the car in front of you would actually brake that we were not able to prove a lot because basically the car, under worst case assumptions, which we kind of had to make, would always lead to a crash. There was also an even more curious thing where what occurred to us as this Euler crashes. So the idea was that the simulation was using an Euler approximation of the differential equations. And depending on the frequency of this approximation, the car would either have a crash or not have a crash. So if we ran the simulation with 10 hertz, which we used for training, the car did have a crash. If we ran the simulation with 100 hertz, the car did not have a crash. So obviously the car learned that it's helpless in this situation. Even if it brakes, it's still going to have a crash. So instead it learned to accelerate in this situation, right? So what we learned from this is that you need to be really careful about basically making sure that your simulation and your model are in sync in the same way that you need to make sure that your simulation and reality are in sync. So this was one of the extensions that we did. And another extension concerns the kind of arithmetic that's happening inside the neural network. So classically, the way we approach neural network verification is we do it as a real arithmetic analysis. So we assume that all the matrix multiplications, all the computations inside the neural network are in real arithmetic because this makes things computationally easier. On the other hand, it's quite different what makes things more computationally easy in the real world, right? In the real world, we usually try to use finite precision arithmetic. We try to use quantized neural networks because that's a lot more computationally efficient. So the question is, can we kind of have the best of both worlds? Can we do our analysis in real arithmetic, but still have guarantees for finite precision arithmetic? And indeed, there is a way to do this. So there's some work from Debashmita Loha, who looked a lot at soundly quantizing neural networks in a way that you have a provable error bound for the evaluation of your network during inference. And so we coupled her approach with my approach, and this basically allowed us to derive guarantees on the real arithmetic level while still getting guarantees for the behavior of the neural network once it's on an FPGA with fixed precision arithmetic. And this has also applications beyond neural network, beyond quantization of neural networks, because it also allows you to, for example, look at other perturbations in your system. More recently, we've been also looking at a generalization of this work, because I would argue that a central aspect of what we did in Versailles was to answer the question, what even is the semantics of the neural network control system? What's the formal semantics? And how can we argue about its correctness? And so we now basically try to learn a larger lesson from this, how we can use this for compositional reasoning about systems with heterogeneous components. And so there we now have a paper on what we call heterogeneous dynamic logic, which basically allows us to have compositional proofs on system correctness. And it also has a formalization in Isabelle. So this will hopefully allow us to have very, very rigorous proofs in an interactive theorem prover about systems like neural network control systems. Now, this paper itself doesn't talk about neural network control systems yet, but this is the target that I basically wrote this paper for. Just to give you an idea, basically the idea is we can have different theories. So we can have a theory which is here in magenta and a theory which is here in blue. And then you can have statements about this. You can have formulas that kind of describe various states in both of these worlds. And you can have programs from both of these worlds. So for example, you could have a neural network here and a differential equation here. And maybe in the middle, you have some other software that is written in C or Java or whatever. And you can reason about all of this in one proof and give one system level guarantee. So this is kind of where I'm trying to go next with this. All right, now to conclude, I told you a lot about neural network verification, how we can use Versailles and Mosaic to derive these provable guarantees. And I try to motivate at least a little bit that we can also use this for heterogeneous AI systems more generally by kind of having a modular way of combining proofs about subsystems. In terms of future work, there's always a lot of engineering and scalability work left to do when it comes to kind of verifying these properties in practice. I might also be really interested in eventually having proof certificates for this verification approach, because obviously, if you were to use this for a system that's actually being deployed, you want to be really sure that you're not only trusting my tool, but that you actually have independently checkable proofs on this problem. There's still work left to do in terms of tooling integration. And also, I'm thinking about maybe extending this to monitoring, because often what we find is that the neural networks that we're trying to verify, they are not actually correct, right? There's actually still safety bugs left. And so the question is, can we come up with monitoring that kind of uses the neural network whenever it's safe and falls back to a monitor in the few cases where we still know the network is doing unsafe things? Right. Now I'm looking forward to any questions, and thank you very much for the invitation and the attention.
Yeah, thank you so much for the presentation. I think in terms of uh, time, we have something like 20 minutes actually for discussion. So um, that um, allows us to get more into the details and also how it might connect to uh, other aspects beyond this work. So we already have some questions in the chat. Maybe we can start there. Bernard, would you like to speak them out?
Sure.
Cool.
Yeah, there's both sort of related. It's a question like how large were the neural networks that you did verify, and do you have some ideas how the verification effort scales with the network size.
Right. So the networks that we did verify were about, so I think the largest was about 300 neurons large. So in terms of parameters, that's about 12,000 parameters. And this is both for the original verification approach and the one for quantized networks. I think so. We did this with very limited compute. I think pushing this to 1,000 or a few thousand neurons is definitely feasible. When it gets larger, the issue that we're fighting is that basically an N verification, even without all the polynomial arithmetic that I've introduced, is already an NP-complete problem. So it's very much an exponential problem in the terms of ReLU nodes in the network. So it's computationally hard. And I guess the one thing that can be said here is that there's at least a few applications where people are also interested in rather small neural networks, especially like in control and reinforcement learning. And here we have a good chance of tackling these things. It's obviously like, unfortunately, it's not something where so far I would see this being applicable to networks with millions or billions of parameters. This is not only the case with this work, but generally neural network verification has a really hard time providing global guarantees for large scale networks. I don't know if that answers your question.
Sure, this very much answers my questions. You mentioned that there was a compositionality approach, and there have been some efforts, I understand, to factor neural networks into smaller units or mostly independent units. Would your method be extendable with sparsity constraints that or work possibly on more modular networks?
Possibly. So I mean, this is a this is something I haven't looked into yet that deeply. Um, I, I've thought about it in the sense of if you have multiple neural networks which have different tasks, let's say a perception network and then a network which does planning or something like that, and you have some interpretable layer in between. You could certainly try to kind of certify or even verify these individual components first and then bring together these guarantees. That's certainly possible with my approach. What I haven't thought about yet is basically if you train a network in a way that it kind of becomes compositionally by construction, if you will. Um, I guess the challenge then is to come up with suitable intermediate lemmas, right? So you kind of need some statement that kind of tells you, oh, like after we run this first component of the network, we know the following guarantee, right? Maybe that's something that's learnable as well. Maybe that's a direction that could be explored. I would have to look into it in more detail.
Great work.
Thank you.
Hi, I had a small question. I am not too familiar with how neural networks work, but you said that in your finding, you found out they kind of work much worse than the tracking systems that are currently in place for avoiding airplane collisions. So relying on these neural networks would actually cause them to crash. So, I mean, what is the future and why are we trying to use neural networks for the vertical airborne collision?
Right. So I maybe have to be careful here. So my point is that the networks that we evaluated were unsafe. This is not a principal issue with using neural networks in this application in general. I think there is ways of basically constructing neural networks that would survive our check and would hopefully be safe. The issue is, or why people are interested in using neural networks here is that in a way, this is an optimization problem. what you want is, on the one hand, you don't want planes to crash, right? On the other hand, you don't want to warn the pilots too often. If you're warning the pilots too often, they're just going to ignore your system. So you basically need to kind of find a sweet spot where you ideally avoid all the crashes while not warning the pilot all the time, right? Because if you could always tell the pilot, oh, please fly down and land, right? But then the pilot would just ignore the system, right? So you kind of need to find a sweet spot between not producing crashes and not warning the pilot too often. And so here people try to use various optimization techniques to come up with such a sweet spot. And what they had before they looked at neural networks were these very, very large lookup tables. So they had lookup tables that were multiple gigabytes large sometimes. And then there is the issue of memory on airplanes, which, to my understanding, I'm not an expert on this, but my understanding is that airplanes for memories is rather expensive because it needs to be certified in certain ways, and I think it also needs to be somewhat radiation hardened. And so the idea was, can we kind of encapsulate this very complex decision strategy into a much smaller neural network, which is then easier to deploy on airplanes in practice. So this was kind of the idea behind it. Yeah.
All right, that's super interesting. Do you think like there is like do you think like an estimate of a timeline where this sort of optimization principle could be applied for these airplane control systems?
I'm not super sure. I mean, this is also a lot of this work was done in the US by various US labs. We basically used this work to evaluate our approach. I'm not personally developing this, so I can't really talk about the timeline. The last time I heard about it, my understanding was that for the current iteration of developing the system further, they actually decided against using neural networks. I think this was around 2020, because there were just not the guarantees there yet to kind of verify this. So I guess maybe we'll have to wait for the next iteration. I'm not sure. Yeah.
Okay, thanks a lot.
So I have a question, which is, um, in your view, what are the bottlenecks for applying this method to novel domains?
Right. So I guess the main bottleneck is you first need to come up with your symbolic model, where you kind of synthesize a control decision or a control envelope for your for your uh, for your abstract system before you can then verify a concrete neural network. There's some very exciting work in this direction where people try to automate this process. So Aditi Kabra, who's a PhD student of Andre Platzer, is looking in kind of synthesizing these control envelopes. And if this gets far enough, then this could certainly kind of alleviate this bottleneck, which then would make it a lot more applicable. The other bottleneck is then kind of computation time, right? Because these problems can become quite complex in terms of the arithmetic. But yeah, right now I would say the bottleneck is still at the level of kind of coming up with these abstract safety arguments first. But you can also use AI there. So people have looked into kind of whether they can, in particular, Aditi Kabra has looked into how one can, for example, use LLMs to auto-formalize differential dynamic logic problems, and how to kind of synthesize these control envelopes in that direction.
I'm curious about this. Will you be able to write the name in the chat of
Yeah, sure,
this?
sure.
In the meantime, I just do want to invite people that are here in this session. If you have questions, do not hesitate. We We have some time now. Thank you.
I have another naive question. You talked about modelplex. So is modelplex and the heterogeneous AI system the same sort of neural network, or like how are they different?
So modelplex is basically a technology that takes your system description in differential dynamic logic, and from it compiles it compiles it down to to this formula which just states which control actions are safe in a given situation. Actually, let me briefly go back. Right. So modelplex is this approach which basically it takes a system description like this one, and then from the control envelope inside the system description, it creates this controller monitor formula. So for example, we might have a control envelope which states either we set the relative acceleration to minus b, or we set it to some arbitrary value under the condition that this arbitrary value is still smaller than b, and furthermore, the relative position is large enough. And then this will convert it into a real arithmetic formula that we can use to check concrete control decisions. This is obviously still a simple example. You can also do this for more complicated controllers. And so, yeah, this is basically what modelplex is. And heterogeneous, the heterogeneous stuff that I was talking about in the end is basically a new logic. So basically the same way that we earlier talked about all possible executions of this hybrid program, here you can talk about all possible executions of a heterogeneous program. And so then inside this heterogeneous program, you can now natively have things like, for example, a differential equation, or like a neural network, and so on and so forth. So it's just it's a new formalism to reason about this in a more rigorous and fundamental way, essentially.
Cool. So they must be having like different applicability, right? Like based on the complexity of the problem. Like you would not need a heterogeneous AI system for setting like the correct acceleration rate, for example, like you mentioned in the beginning. Or
Right. So
is it, yeah.
the idea is that with this new logic we can describe many more properties or many more systems in a way than we were able to before, hopefully. I mean, so far this is mostly a theoretical, or like a theory paper. We establish a calculus and relative completeness guarantees and so on. But the idea is to for me, the next step would be to bring this into practice. Yeah. And there I also hope to build some AI support to kind of, because then you also, like, if you reason about a large system where you have different components, you will also basically have to reason about the individual components and derive guarantees for these first. And my hope is that there we can also use AI.
Yeah, that sounds like fairly complicated to actually implement, but I mean, it sounds like it could be quite useful if it could be done. So yeah.
Yeah.
So
I think there's another question.
Yes, in the chat, there's a question. How well do the methods work if you have an imperfect world model, for example, dynamics with latent controls, other actors, inherently stochastic processes?
Right. So I mean, like one thing that we already looked at is this gap between real arithmetic and the arithmetic in the real world, which usually is something like finite position arithmetic. So we can reason about certain kinds of perturbations with this. We can also reason about, let's say, imprecisions in sensing and imprecisions in actuation using this approach. There is still limitations in terms of the kinds of imperfections that we can look at. So for example, Latency is a little bit more complicated because then there's like basically if you observe a different state than the state that your car is actually already in, you kind of need some kind of synchronicity in your system. That's more complicated to model. One thing I want to emphasize in that direction, though, is the way we formalize these hybrid programs. We usually only give an upper bound on the cycle time. So basically, that means one kind of imperfection that we're already accounting for is that your cycle times might deviate across iterations, right? So maybe in your first iteration, you have 0.1 seconds from the last control decision to the next one, and in your next control cycle, you have 0.12 seconds. This kind of thing we can easily model with this. Regarding stochastic world models, this is something we haven't looked into yet. So that would certainly also be interesting, but so far we only support deterministic world models. Or like non-deterministic world models, but not stochastic ones. I should be precise here. So we can have non-determinism, but we can't like quantify that non-determinism in a probabilistic way, only possibilistic.
I'm sorry, but I don't really get how would that work, like non-determinism versus a stochastic processes. Like you already know the possibilities that could like happen, or how does that work?
Right. So okay, I guess yeah, let me try to rephrase that. The point I'm trying to make is let's say you have some noise variable, and you know that noise variable has like a uniformly random value inside some range. What we can do is we can just assume the worst case and say, okay, this variable is going to have some value inside this range. We can't make probabilistic statements in the sense of your system is going to be safe with probability 0.9999 because we can't account like for actually this smaller range of the variable already accounts for almost the entire almost all possibilities. Does that make sense?
I mean, kind of. So we cannot like put a number on an event rather than like have only the range of events that could take place.
Yeah, yeah. Maybe uniform distribution is a bad example. So let's say we have a Gaussian distribution. This would be really bad for our approach because essentially if we have a Gaussian distribution, we have to, like our approach would assume all possible values. So the entire value range from -infinity to +infinity versus a probabilistic approach could only account for, let's say, 3 sigmas or something like that, and then give a quantitative guarantee on that.
Right. Makes sense now.
Out of curiosity, I'm curious about if you have ideas of like envelopes that you think could be covered by this approach, or an extension of this approach that you would be that you would think that like could be covered and that would be most interesting.
Let's see. So in terms of envelopes that can be covered, I think the most natural target is any kind of neural system where you have a reasonable understanding of your input space, or at least can like in some way come up with the reasonable understanding of your input space, right? The better you can put names to the input dimensions of your network, the better you're going to be able to come up with your differential dynamic logic model of the system. right? So I had this example with relative position and relative velocity, right? There, it's really clear what the symbolic meaning of this is. The more things become abstract, the more complicated it gets to kind of apply this approach in its current state. I think here it could also be interesting. I've thought about this before, but haven't really gotten around to doing this yet. I think it could also be interesting to, for example, look at neural ordinary differential equations, which kind of let you learn dynamics of systems. If one were to figure out how to kind of use this approach with a neural ordinary differential equation system, suddenly you could look at this for different kinds of systems where you have a less clear understanding of the variable space essentially. So that might be one possible extension. Another possible extension, which was already mentioned, is stochastic processes. So there is a variant of differential dynamic logic that does support probabilism. So that could also be a possible extension at some point.
Thank you. I think we actually might have time only for one last question. If anyone hasn't asked yet, this is your opportunity.
I just want to say it's a great talk, and I have to run. So thank you so much. Appreciate this. Yeah.
Thank you.
Mhm.
All right. Well,
Very interesting. Thank you.
Thank you.
thanks so much for the presentation, and thanks everyone for having been here.
Thanks.
Ciao.
Yeah, thanks very much for the invitation. Was happy to be here.
Awesome. Ciao.